Okay folks, we're taking a well-deserved break from differentiation and looking at its much maligned cousin, integration. From last year we've essentially got one rule, which is that if we have x to the power of 3 for example, we know we can integrate that by increasing the power and dividing by the new power. But that really limits the things that we're able to integrate, and so the first thing that we need to do is we need to incorporate all of the new differentiation rules, because differentiation and integration are opposites to each other. They are inverses, I suppose, of each other. If you can differentiate to get x to get y, then you should be able to integrate y to get back to x. So let's look at some of the standard results we found in differentiation and see how you might rephrase those as standard integration results. So the easiest one is e to the x. If we integrate e to the x, we get e to the x, because if we differentiate e to the x, we get e to the x. Similarly with logs, if we differentiate ln of x, we get 1 over x. So flipping that around, if we integrate 1 over x, we get ln of x. Don't forget there's plus c, by the way, that still exists. And so we can sort of go through the list of things that we've differentiated and just flip them around and say, but if we integrated that result, we'd end up back at where we started. So integral of cos is sine. Integral of sine is minus cos. Now that's not quite saying exactly the same set of phrases, but obviously that minus sign can be transitively applied. We introduced some trig differentiation, and we can use that in reverse as well. So sec squared integrates to tan, sec tan integrates to sec, cosec cot goes back to minus cosec, cosec squared goes to minus cot, and then this is the one that we already know. If we integrate x to the power of n, we increase the power, divide by the new power. So when we say standard integral results in year 13, these are the ones that we refer to, and some of these are given to you in the exam. So it's worth knowing that roughly here, I think, is the cutoff. Anything below that line is given to you in the exam in a formula book. Everything above that line is things that you need to learn. I'd well recommend just writing down that list somewhere though, because it's a useful reference guide. So let's look at applying some of those standard results, and this is more a case of just looking up the right thing from the table. So the first thing we've got is 4x to the 7, and that's something that we already do know how to integrate. That's just x to a power, so we can just increase the power. So this would go up to 4x to the 8, and then we divide by that new power, and don't forget the plus c. Now we could, I suppose, simplify that to x to the 8 over 2 plus c if we really wanted. Numbers like 4 at the front don't have any bearing on the integral. The integral of 4x to the 7 is 4 times the integral of x to the 7. You can split them apart, no problems, and that's the only things you can split apart like that. What about the next one? Well, if we want to integrate this, we should do them one at a time. So the first thing we should do is e to the x. Now, according to our rule here, if we integrate e to the x, we get e to the x, so that seems fair enough. So if we integrate 3e to the x, we get 3e to the x. What about sec squared x? That's this one here, isn't it? That goes to tan, but this is minus sec squared, so it's going to go to minus tan. And then we can stick our plus c at the end. You don't need to stick in a plus c for everything that you've integrated, just as a final constant at the end. What about the next one? Well, the next one looks awkward, doesn't it? It's not on our list. We can't see cos over sine squared anywhere there. But we can rewrite this. We can rewrite this as cos x over sine x, I guess. Yep, cos x over sine x times 1 over sine x. Now, why would we do that? Well, that's equal to cot x cosec x. That is very definitely something that we know how to integrate. So the integral of that, according to our list, is just minus cosec x plus c. So if you've got something that looks unfamiliar and it's trig, try and rearrange it into one of these forms. Like I say, you get given these 4 in the exam, so it's useful to just look at those and think, well, what is this closest to? And the last one, again, similarly annoying. What we'd probably want to do is expand. We don't have an integration rule for like brackets or anything yet. So we'll do that. Cosec squared cos, and we've got cosec squared tan. Now, none of those look like things that we can integrate, so we shall break them down into coses and sines and see if we can rebuild them. So this is overall here cos x, and then cosec squared means 1 over sine squared x. And then the other one, well, cosec is 1 over sine squared again, and tan squared is sine squared over cos squared. So can we do anything with that? Well, we can certainly cancel out those sine squareds there. And this one on the left, that's the same as the one we just integrated. That's cos over sine squared, isn't it? So we could rewrite the left-hand side one as cot x cosec x in the same way that we did with the previous question. And then 1 over cos squared, which is what's left here, is the same as sec squared x, which is something that we can integrate. So we're going to use both of these integrals here, and we can go to the integral of y dx is equal to minus cosec x. What's sec squared go to? Plus tan x, and then don't forget plus c. So yeah, this is a case of looking at a table and rearranging any trig that doesn't look quite right. So it's obviously important to remember that definite integrals exist as well, and we can use exactly the same rules as we did last year. Here we're trying to integrate 1 plus x to the 5 all over x, and that isn't a standard result. We don't have a rule like a quotient rule for integrals with fractions yet. So what we'd want to do with this is split the numerator up and see if it works into something that we can use. So we've got 1 over x plus x to the 5 over x. Now, 1 over x is a standard result. X to the 5 over x can be simplified. So let's do that. And x to the 4 is a standard result. It's just x to the power of n. So yeah, we can integrate this. Excellent. So let's do that. 1 over x, that integrates to ln of x. And x to the 4, that would be a case of increase the power and divide by the new power. Do we put a plus c on? No, we don't, because this is a definite integral. And with definite integrals, what you need to do is substitute in the limits of the integral. So substitute in the 5, substitute in the 1, and subtract the latter from the former. So we're going to have ln of 5 plus 5 to the power of 5 over 5. A lot of 5's in this. Take away ln of 1 plus 1 to the power of 5 over 5. Can we simplify anything here? Well, ln of 1 is just 0. Log of 1 is always 0 for any base. And then we just want to try and evaluate some of these large powers that we come up with. So 5 to the 5 is 3,125 divided by 5, 625. So we're going to have ln 5 plus 625 take away, and then 1 to the 5 is just 1, so take away a fifth. Simplify that one more time. We could say we've got ln of 5 plus, I guess, 624 and a fifth. Well, let's say 624.2. Can we do anything with that? Well, we could come up with a decimal answer, but that's the exact answer. That's as accurate as we need or want to be. Okay, for the second one, there's a really important point here that if you're integrating anything to do with trig, so any cos, sine, etc., and you're going to substitute limits into it, you need to be working in radians. So the first thing you'd need to do if you saw this question is change your calculator to radians if it wasn't already. Second thing we need to do is we need to look at our list and think, is there any standard results here? And yeah, we've been quite kind this time. So we've got a cos and we've got a sec squared. So we can go straight into integrating this. We can say that we have got, well, sec squared goes to tan x. Just going to point at this and say radians. Radians. And cos goes up to sine. We don't need a plus c because it's definite. And what we're going to do is we're going to substitute in pi over 8 and 0. Okay, so let's do that. So we need to substitute in pi over 8, we need to substitute in 0, and we need to see what we get. Okay, so can we get rid of anything? Well, tan of 0 is 0, sine of 0 is 0. And these aren't really standard results that are left, so we can't put these as nice fractions. I suppose we could fiddle around with some special triangles for a while, but this is fine. all I'm going to say is that tan pi over 8 is about 0.414 and sine of 0.8 is about 0.382. Should be a minus, by the way. Take away 0, so our overall result is 0.79. Ooh, looks like it rounds up to 0.797. So there you go. Make sure you look at your standard list. If you've got any numerators, try and split them up, and just make sure that you're not assuming there's like equivalence of differentiation rules that you haven't seen yet.